Ever wonder what's really going on inside an AI when it's writing a poem or sifting through data? Well, it's not magic, it's code. Today, we're going to peel back the layers and look at the actual building blocks that make modern artificial intelligence tick. So let's pull back that curtain and see how it all works, right from the very beginning. You know, it all boils down to one fundamental problem. At their heart, computers are, well, they're really simple. They only get on or off, ones and zeros. That's it. So how on earth do we get from that simple binary world to a machine that can understand the complex text you're reading on your screen right now? This is the central puzzle that this entire stack of technology is designed to solve. So our first hurdle is basically translation. We've got to find a way to take all of our letters, our symbols, even our emojis, and turn them into the only language a computer speaks, numbers.
And the tool for that translation is something called character encoding. The easiest way to think about it is like a giant universal dictionary. For every single character you can possibly type, a capital A, an exclamation point, even an accented ah, this dictionary has a unique number assigned to it. It's the essential bridge connecting our human world of text to the computer's world of numbers.
Now, this dictionary has definitely evolved. Way back in the 60s, we had ASCII. It was great for English, but it only had 127 characters. As computers started going global, we got extensions like ISO 8859-1 to handle more European languages. But with the internet connecting everyone, it was obvious we needed one single universal standard. And that brought us to Unicode in 1991, which had this huge, ambitious goal: encode every character from every language in the entire world. Today, UTF-8 is the undisputed champ. It covers over 143,000 characters from Unicode. But here's the really brilliant part: it's backward compatible. The creators made sure that its first 128 characters lined up perfectly with the original ASCII. This was a genius move, because it meant all those old text files and websites from decades ago would still work perfectly on modern systems. Talk about future-proofing.
Okay, so all our text is now just a long stream of numbers. But, a jumbled stream of numbers isn't very useful. We need to organize it, to put those numbers into neat containers a program can actually work with. And when it comes to organizing data for AI, one language is king: Python. And inside Python, two of the most basic containers you'll find are lists and tuples. They look pretty similar, but they have one absolutely critical difference you have to remember. A list, which uses square brackets, is mutable. That means you can change it whenever you want. But a tuple, with its parentheses, that's immutable. Once you create it, it's set in stone. So with a list, you get flexibility. Let's say you create a list called X with the numbers 1, 2, and 3. You can just go right back in later and change the first element, swapping out that 1 for 99. No problem at all. But if you try to pull that same move with a tuple, nope. Python stops you cold. It throws a type error. And this isn't a bug, it's a feature. That immutability is a guarantee. It promises you and the computer that this chunk of data won't be accidentally changed somewhere down the line. And for keeping your data clean, that's incredibly important. All right, so we've got our numbers organized, but there's a problem. A big one. Modern AI doesn't just work with a few numbers. It's crunching billions of them all at once. And our nice, neat Python containers, they're just too slow for that kind of heavy lifting. We need a speed boost, a massive one.
And I know what you might be thinking. Hold on, isn't Python already a powerful language? Can it do math? And yeah, it absolutely can. So why on earth do we need a whole separate library just for number crunching?
The answer comes down to one word: speed. A standard Python loop is like trying to move a whole beach by picking up one grain of sand at a time. Yeah, you'll get there eventually, but it'll take forever. For AI, we need a way to move the whole sandbox at once. And here's what that looks like in practice. The slow way is a classic Python for loop, where you're telling the computer, okay, go to the first number, add 10. Now go to the second number, add 10, and on and on. The fast way is with NumPy. You just say, take the whole bunch of numbers and add 10. Boom, done. This is called vectorization, and it's ridiculously faster, because NumPy isn't doing it in Python. It's handing the job off to super fast, pre-compiled code that's written in a much lower level language. So now we have lightning fast math. The next step is to actually assemble all those math operations into a structure that can learn, a neural network. And this is where a framework like PyTorch comes in. Honestly, it's like the ultimate Lego kit for building AI models.
The
most basic building block in PyTorch is the tensor. Now, at first glance, it looks and feels almost exactly like one of our fast NumPy arrays, but it's got a superpower. It knows how to run on a graphics processing unit, a GPU. This lets it perform thousands or even millions of calculations all at the same time, in parallel. And that is the secret sauce for training the gigantic neural networks that power today's AI.
And if tensors are the raw material, this brings us to the actual Lego bricks themselves, the PyTorch module. You can think of each module as a self-contained piece of a neural network. It could be a whole layer of neurons, a specific math function, any component you can think of, really. And building your own custom Lego brick is surprisingly straightforward. You just need to define two main things. First, in a method called __init, you basically gather all the smaller pieces you'll need. It's like dumping all your Lego bricks out on the floor before you start building. Then, in a second part called forward, you define the exact path the data takes as it flows through those bricks. You're literally writing the instruction manual for how to snap your component together.
Okay, let's zoom out and take a look at the whole picture now. We've gone from the most basic, simple idea of representing a character all the way up to a powerful framework for building a machine that can actually learn.
The whole process really flows in 4 logical steps. First, we encode our text into numbers using UTF-8. Second, we organize all those numbers into useful containers using Python. Third, we use NumPy to do all the heavy math at incredible speeds. And finally, fourth, we use PyTorch to assemble all those operations into complex neural networks that can learn from data. Every single layer of this stack is absolutely essential. And this really gets to the heart of it. Python didn't become the language of AI just because it's easy to read. It's because of this incredible ecosystem that grew up around it. It's the combination of Python's simplicity with the raw, brute force power of libraries like NumPy and PyTorch that really ignited the AI revolution. So, it turns out AI isn't really magic after all. It's a tower of incredibly clever ideas, just built one on top of the other. And now that we've seen the code behind the curtain, the only real question left is, knowing how the trick is done, what new magic are we going to create with it?